Okay, hello. Yeah, thanks for the introduction, and thanks for sticking around to the bitter end of this. Yeah, we're going to learn all about small angle X-ray scattering.
Started recording?
Yeah, I think I did. Yeah. So you already have been to the c.l.s. You've been on the tour yesterday. You've seen maybe where Brockhaus is, and you also saw CMCF as well. So yeah, I'm coming from the Brockhaus sector. It's 3 hard X-ray beamlines that have been in user operation since 2020, so it's pretty recent. Beatrice showed this slide earlier. This is an overview of our 3 beamlines. I spend most of my time on the low energy Wiggler beamline here, but we all bounce around. It's a big group of people. It's a busy place. We do a lot of techniques. If you want to know a little bit, I'm not going to talk too much about the beamline itself. If you want to know more about the beamline, there's a recent paper out in Journal of Synchrotron Radiation. You can learn all about it there. I'm mostly going to talk about the SAXS end station, which is mostly based, well, most of the development has been done at the low energy Wiggler beamline, but in the future we'll do more work at the undulator beamline too, and maybe even the high energy Wiggler beamline at some point. So it's a fairly new end station. We've really only been up and running since 2021, and there's no dedicated SAXS beamline at c.l.s. A lot of synchrotrons will have their own beamline totally dedicated to SAXS. We're more of like a multi-purpose facility that also does SAXS. So some of the basics. Here is a demonstration of like X-ray scattering from a single atom, right? So if you have X-ray interacting with an atom, one thing that can happen is you get less X-rays coming out. That's photoabsorption. We don't care about that. What we're really interested in this workshop is elastic scattering, where X-rays pass by the atom and they cause the electrons in the atom to oscillate, and those electrons re-radiate the wave out in all directions. So, and there's no change in wavelength. You can measure this with maybe putting like a little diode behind your sample and defining some scattering angle, 2 theta. And if you swing your diode around the sample, you can work out a scattering pattern. And these are the atomic scattering factors for several atoms. You've seen all this before in other talks, but what you can notice is that as you have more electrons on the atom, they scatter stronger. And it's a more normal relationship than what Graham showed with the neutrons, where it's all scattering all over the place. It's pretty linear for X-ray scattering. And of course, here on Earth, like atoms are bound up in molecules and other things, and they're often ordered. So if you have X-rays going into this ordered structure, now you get scattering off of all the electrons in the atom, or sorry, in the molecule or in the structure. And you get constructive and destructive interference. So the wave that's bouncing or that's scattered off the top layer is out of phase in this example with the wave from the bottom layer, so you don't see anything on your detector there. But if you move to another angle, now the wave from the second layer is in phase with the top layer. You get constructive interference, you get Bragg diffraction. I'm sure you should all know this one by now. You get constructive interference channeled in specific directions based on d-spacings in your sample, ordered planes of scatterers within your sample. And this is what you'd see for a normal like powder diffraction pattern. So you already know this. X-ray scattering and diffraction reveals structural order within materials. You might only be thinking so far about the atomic scale, but this can go up to the 150 nanometer length scale, actually. Well, how is that? Well, if we start from our powder diffraction, what we know about powder diffraction, we're scanning all these ranges of these angles in 2 theta, and the angles are such. This is just Bragg's law plotted for 2 different wavelengths here. The angles that we're looking at usually are such that we're looking at distances that are on the atomic scale or between atomic planes. But if you were to just measure at a really low angle, like less than 5 degrees, now you're sensitive to d-spacings in the range of 1 nanometer to 100 nanometers or even a micron if you go low enough. And what's up there? What kind of order is there? That's what SAXS is all about. So just in one line, small angle scattering is useful to probe relatively big things with X-rays. Not atomic distances, but other things. And what kind of other things are we talking about? Well, SAXS finds broad applications. in systems like drug delivery and pharmaceuticals. I'm going to have a detailed example of this later. Protein size and shape, Bob talked about this on one of his slides, I think yesterday. But also things like food science. A lot of components of food happen to be ordered on the nanometer scale, like starches have this semicrystalline and amorphous banding that happens to be on the nanometer scale. You can look at that with SAXS. All types of biomacromolecules also order on the nanometer scale. And of course, all things nanoparticle have been studied by SAXS. The things that you can really get out of SAXS are the packing and ordering, particle size and size distribution, and a scattering shape. I'll show some examples later, but this is just to give a flavor of what's coming. And now, how does this fit in with other related diffraction techniques? Well, I've plotted here some of the other techniques that we've seen, the powder diffraction, pair distribution function. And it's all on the scale of well, scattering angle, but it's also in terms of D or in terms of this thing called Q, which I'll talk about on the next slide. But SAXS is kind of, it's a continuation. It picks up where powder diffraction leaves off. And actually, there's certain beamlines that do SAXS and what's called WAX, which is really just powder diffraction of an area detector. So the ranges overlap. But again, with these other techniques like powder diffraction and pair distribution function, it's really focused on atoms and interatomic distances and bond lengths, whereas SAXS is more about the nanoscale or intermolecular things. And it also bodes well with microscopy techniques. The range that SAXS, the size range that SAXS is sensitive to is in the range of microscopy like TEM or scanning transmission X-ray microscopy. But instead of, you don't have this really small field of view with SAXS. You're averaging over the whole beam footprint. So you're averaging a relatively huge volume compared to what you can see with these other microscopy technies. I added this slide last night because someone who will remain nameless was like, "Hey, Adam, what's Q?" So SAXS is usually shown as intensity versus a Q value, and Q is momentum transfer. So photons, even though they're massless particles, they have momentum. Which has a magnitude and a direction, so it's a vector. And you can express that in terms of this wave number k. And in this Ewald sphere depiction of diffraction, momentum transfer is the difference in momentum between the incident photon and the one that scatters out there. Somehow that photon that came out got some momentum, and it came from the scatterer there. So somehow momentum was transferred to it. Q is just that difference there, and you can express it in terms of this equation here that relates the scattering angle to and wavelength to Q. It's also related to Bragg's law by this other equation here, 2 pi over d. So this is what Q is, and you can normally powder diffraction is expressed in 2 theta versus intensity, but you can also plot it as Q versus intensity or as D versus intensity. They're all just related to each other. So, but for most of this talk, the scale on the bottom is going to be Q, and sometimes it'll be 2 theta. But that's what that is. Okay, so how do we go about measuring small angle X-ray scattering? Again, starting from powder diffraction. So just like powder diffraction, there are also lab-based SAXS instruments that use lab sources. And why do it at a synchrotron rather than a lab source? It's the same reasons you would do powder diffraction at a synchrotron than at a lab source. You get way more flux, so you can pick out weakly scattering objects, things that you might not ever see because they're buried in the noise. In a lab source, you'll see in a synchrotron experiment. As Beatrice showed, there's generally more room for like a flexible setup or in situ cells. People at the synchrotron will try to bend over backwards to accommodate your crazy experiment. Maybe not so much at a lab instrument that has to be a workhorse. You can choose, you have the choice of many wavelengths, usually. And you can also do things like diffraction mapping or SAXS mapping. If you have your beam focused down to a small enough point, you can raster scan your sample through there and build up like a diffraction-based contrast image. That's something you could never do at a lab source with any kind of competitive spatial resolution anyway. So how are we going to measure this? Well, I'll just start with our powder diffractometer. Oh yeah, I forgot about that example. Oh, what I was going to show you. Oh, this, okay. Oh yeah, that's fine. So starting from powder diffraction, here's our powder diffractometer in low energy Brockhaus beamline. Some of you may have seen it yesterday. We put some samples on there. We scanned from 2 theta, 3 degrees to 80 or so. And we have this linear strip detector, which this is the best thing going, I think, for powder diffraction right now. There's ones that give you better Q resolution, but this is very common. And has these 50 micron strips that are 8 millimeters wide. And eventually we're going to have 8 of them. We'll have a robot, and it's going to be really great. But can we just do SAXS with this thing? Can we just move the detector to a low angle and away we go? Well, not really. And I'm going to rip off a slide here from my colleague there, Bob, or my trivia night partner, Bob Von Driel. It's this axial divergence thing. So the device share, it comes off as cones, right? And as you go to smaller angle, these cones get tighter and tighter and tighter. And what we kind of have with this detector is a bunch of little slits, and you're trying to scan a horizontal slit thing over a round thing that's getting smaller and smaller. It just isn't going to work. We need something different, and we need something more like our wide angle X-ray scattering setup, which uses this big it uses this big area detector with little tiny square pixels, which is nice. So we can do diffraction that way. It's just like powder diffraction, but it's in 2 dimensions. It's really great for looking at texture and things like that, but you can just think of it as powder diffraction with an area detector. This is lanthanum hexaboride measured with our wax setup with PXRD, and they're basically equivalent. You can do a radial or azimuthal integration and lay one on top of the other. But now with this setup, we have these square pixels, so we don't really care about axial divergence as much. And we can get to a lower Q value than we could before. We have this beam stop that stops the direct beam. But now we can get to a 2 theta angle or a Q value that's smaller to reveal a D spacing that's like 3.6 nanometers. So that's getting there. But what we really do is take that same setup and we move the detector back even further. So now we kind of have the same diameter beam stop, but it's like 2.5 meters, well, almost 2.5 meters downstream. So things that before were like hiding behind the beam stop, literally, you can see them now because you're so much farther back. You can see a much smaller angle. And again, this is just think of it as an extension of powder diffraction. You're just moving the detector back. You can see a few more features that you couldn't see before. And you can get even fancier with this. You might imagine well, how far can we move the detector back? The longer, farther, the better. I mean, at one of our beamlines, at the low energy beamline, we hit the wall. We can I've actually made a longer tube for our undulator beamline that's 4 meters long, so we can get to D spacings of, probing a Q of 0.0027. We can see much bigger things. We're eventually going to test this out there. But here's even an even crazier thing. At the Brazilian synchrotron, they have a vacuum tube that you can walk into that's 14 meters long. You're going to have a gigantic detector to do SAXS and wax at the same time. But this is taking it to extremes. Okay, so more in depth about our instrument. So you can't just have this detector far back. That's not enough. There's other conditions. You need to have a really low divergent beam in order to measure these really tiny angles. It has to be really 200 microradians or so, and we do that with slits. So there's this really great 3-pin layout, which is what everyone doing SAXS competitively uses now. You have a beam-defining slit up front, which sets your beam size. You have an anti-scatter slit, which kind of just cleans up what's the scatter from the first slit, and then you also have a guard slit right close to your sample. The whole point is just define the angles really, really well. You want to have just a really parallel beam. And not only do you need to have this particular slit arrangement, you also get scattering from the slits themselves. So you have to modify them to have less scatter. And we do that by gluing little single crystals at a specific angle for our specific wavelength and specific distance so that if they do scatter, it's at angles that are nowhere near our detector. And it really cleans up the beam nicely. So that's all the upstream part up here. Then the sample region is over here. And it's like this little gap. We want to minimize the air gap between all these components because the air gap also scatters. So we put our samples in this location here. And then we have a vacuum tube downstream of that. And so, yeah, in this vacuum tube, we have our little beam stop flange here. There's a beam stop. There's also this other beam blocker thing shown here, too. This is all under vacuum. We have this sealed with a capped on window, which I don't know how this thing doesn't break, but it doesn't. Then this is what kind of the detector image that you see for when there's no sample in place. You have the beam stop in the middle there. You can kind of see the outline of this tube and the beam stop stick there. So this is the whole setup. In total, it's like 8 meters long from the upstream slit all the way to the detector. So it's really long. Again, it's to really define those angles because we want to look at really small angles. Okay, so how do we compare samples? How do we collect data? Do the data workup? Anything that's going to fit in that little gap there, I would be willing to give it a shot. Like a lot of times we just have these like capillaries with powder, just like our powder diffraction measurements typically does. We can have some stages that move a tray of samples. This is a tray of liquid capillaries here, liquid-filled capillaries. We have a multi-sample changer. We can put like little bits of chocolate on there, and yeah, it's a fun one. So whatever, and we're doing more in situ stuff now. We actually did like a first kind of heating experiment with the guy from Scott's group, where we're blowing hot or cold gas on the sample to do temperature control. And we can also function in grazing incidents as well. Like as Beatrice showed, grazing incidents is great for sample surfaces. So we can line up a bunch of flat samples on our sample changer, typically silicon wafers or glass slides. And yeah, we can do liquids. They generally need to be pretty dilute though. Actually, it's good to bring a range of concentrations, and I'll talk about why in a bit, but that's how we would normally, that's what the sample prep looks like. And then the acquisition is pretty straightforward. Usually we just take our sample and we scan it through the beam. This is like the output of the photodiode at the back of the SAXS tube. So we scan it through. This little dip is like how we know that the sample's actually in the beam. And we just move it to that spot and we collect an image. And that image might take a second or half a second, or maybe the most I've seen so far is like 90 seconds at the low energy beam line. And that's your raw data. That's your raw SAXS pattern. And then, also when you come to do measurements, because I know you're going to come and want to do SAXS now, you want to note down the wavelength and the detector distance. That becomes important for when we calibrate the detector. I think there's probably an in-person demonstration of how you calibrate a detector with g.s. It's the same procedure for SAXS. We have a sample or standard silver bohenate. It produces these really nice rings, which are at known positions. And you'd enter in, this is where you'd enter in your wavelength and detector distance. You'd fix the wavelength because we know that one really well. You'd refine the beam center and detector distance and tilt angles. And then you would apply that, you'd save those parameters and apply them to your data that I'm going to show next. There's other options. Now I should have cut these off here because I know apparently the Nika one actually does the conical sections that g.s do. So that one's good. But those other two, yeah, I'll cut them for the next presentation. Okay, so then there's some corrections you have to do to the data. So this is the scattering pattern for 100 nanometer diameter polystyrene spheres in water. And you don't really see much of anything. In fact, don't be surprised when you come to a SAXS experiment and you're like, hey, where's my peaks? Or what does my sample look like? It's usually pretty featureless. There's only a few samples where you see something that's really nice and defined. It's often only after you do a background subtraction. Just like you do like in UV vis spectroscopy, you'd have a blank cuvette with your buffer. You need that in order to subtract off from your data. And then what you're left with is the scattering from your sample itself. You don't, at least at the c.l.s, you don't have to do any corrections for intensity because we're in this great thing called top-up mode now where there's no beam decay over time. It's really great for doing normalization. And our detector images are already corrected for dark current and flat field and things. So then, yeah, you get this corrected image. And you can do the azimuthal or radial integration and pull out your scattering pattern as shown here as a function of Q. And sometimes in SAXS data, you'll see like this high Q range is kind of noisy. It's usually because the blank and the sample, it's almost the same scattering power at the high Q range. So this is like a bunch of noise often. So that's why it usually looks like that. Okay, so now some examples. So we are a pretty new end station, pretty new beamline. We don't have anything published yet for SAXS, but all these examples I'm going to show are from groups that are using the beamline now that have published things from other facilities. So it's real data with their permission. So, but before I do that, I'm going to talk about the origins of the SAXS signal. So where does this actually? What is this? Where does it actually come from? So it's two things. So the intensity here as a function of Q is proportional to P of Q times S of Q. P of Q is the form factor, which originates from the individual particle scattering or scattering within the particle itself. It's something that you only really observe when you have like low concentrations. You really need kind of dilute samples. And you don't really see peaks. You see these kind of oscillations in there. And this kind of encodes most of the size or polydispersity or shape information about your sample. The other part that contributes is the structure factor. And you can kind of think of this as Bragg peaks. It's coming from interparticle interferences or arrangements, correlations, distances between particles, and generally occurs at really high concentrations of solids with 90% loading or something like that, where you see peaks, and it's really, you can think of it as an extension of powder diffraction to some extent. So the first set of examples I'm going to show are more like the structure factor things, then we'll get more into like what is that thing. Okay, we have several groups that are doing solar cell research involving these like quantum dot materials or these nano perovskites. These are little nanocrystals where you can tune the size and tune the band gap of them to be perfectly in line with the solar spectrum and generate really efficient excitons. And you can make a device that turns solar power or sunlight into electricity. And the way this is fabricated is you spin coat a bunch of drop cast and spin coat a bunch of these quantum dots and evaporate some electrodes on top and then do some electrical testing. Here's like an SEM image of this thing and a TEM image of the particles inside. So the performance of these devices is really influenced by not only the particle size and size distribution, but also how they pack and this interparticle distance here. So groups will come with a whole whack of samples and with different ligand exchange cycles or rinsing steps, and they want to know what is this interparticle distance here. So we would take the sample and just like Beatrice showed earlier, we like do a height scan. So this is feedback from the diode that's inside at the back of this SAXS tube. So we scan this tray through the beam. We look at where it cuts off. We kind of move it to that position where it's like half in the beam, half out. And we do a rocking curve of the theta. So this is like it's blocking the beam, it's passed, and it's blocking again. So we kind of set the height and angle just right. And then maybe we move the angle to some, well, whatever they want. They're usually really low angles, like theta 0.003. And so it's a grazing. This is a grazing incidence SAXS pattern. And so what you can see here is like this is the edge of the SAXS tube. This is a signal from the capped on entrance window. So I wasn't using the silicon nitride at the time. They didn't really care because their samples scatter really strongly. What's really interesting is this part in the middle here, this sword-looking thing. So there's a lot of information you can pull out of this pattern. The first thing is this ring here that you can see more in the transmission part than the reflection part is related to the interparticle distance. So by doing the integration here, you can this peak shape or the peak position is related to the interparticle distance, but it's the interparticle distance averaged over the whole beam footprint. So it's not just like the TEM image where you're getting, oh, this is really my, I'm going to zoom in and take the best TEM image ever. It's actually averaged over a whole bunch of particles. So there's no chance that you can get confused with what part of this is this really representative of my sample, or is this a real thing. So not only do they look at the position, but the width of the peak says something about the size distribution. And so that's the main thing they're interested in. But also what else is encoded in here is there is an X-ray reflectivity curve that's kind of embedded in this top part here. So this is mostly reflection off of the substrate. But there is an interference pattern between the reflection off the top of the film and off the substrate. And when they interfere, you get this frequency, you get these Kiesig fringes, and you can pull out a film thickness from that part of the image. And lastly, you can see there's this weird banding here. These are called waveguide modes, where it's multiple X-ray reflections that are going off the top and bottom and off the top and bottom again here. So you can see 3 different bands. So there's 3 different reflections in there. That can tell you about roughness. For them, it indicates that it's a really nice, flat, high-quality film. You wouldn't see this unless the film is super, super flat. So, and yeah, if you wanted to get some depth information, you can adjust the grazing angle too. But this is really more than I tell them, oh, well, you can see these things. They're like, we just want that. Just tell us that number. Okay, food science. So there's people that are looking at chocolate. Why is chocolate great? As if we didn't already know. But so chocolate is affected. The properties of chocolate are affected by this distribution of cocoa butter polymorphs. There's several different orientations that cocoa butter can crystallize in, and it's this form 5 here. That's the really good one. It has properties where it's super glassy looking. It's hard. It snaps easily. It doesn't melt easy. Has a great mouthfeel. So that's the one that people want to produce, and they produce this now by doing a tempering process, where you cool the chocolate and you kind of work it around and you heat it and you cool it to guide the crystallization to this 5th polymorph. But what the group here of Alejandro Marangoni found is that they can just take this one little additive that actually is removed early on in the chocolate processing steps, and they can add it at a certain time in the process, and it actually templates out this 5th polymorph preferentially. You don't have to do any of this time and labor intensive tempering. So they published this, but they had no idea why this little phospholipid makes a difference. So they used SAXS to kind of learn about what might be going on here. So yeah, they lined up all the chocolates. We did a lot of fun experiments with this. We got the SAXS pattern and the radial integration, and you get these peaks here, which are related to the cocoa butter polymorphs. You can figure out how much of what polymorph was there. But they took it one step farther, and they did some crystallite size and strain analysis. This is the same thing you would do with the powder diffraction pattern, like a Williamson Hall plot. So they were able to determine all these peak widths and plot them and figure out crystallite size and strain. And I think what they learned is that there's some sort of inverse micelle forming here, which is related to this tiny peak, and that thing really is templating the crystallization. So, but just to show you that one way you can think about SAXS as an extension of powder diffraction, you can sometimes apply the same formulas from powder diffraction to SAXS, because it's just the same thing but lower Q. There's a lot of self-assembly in biology. This group here of Matthew Harrington, they're interested in all these weird biofibers. They brought us some muscle threads. There's these threads that the muscle puts out to stick onto the rocks, and they're really tough, and they have this ability to stretch and heal. But it's kind of confusing because they're acellular. They don't have any way to repair themselves. They're mostly just proteins. So how do they actually heal themselves without being alive? So they did some in situ SAXS. They did some actual stretching and bending of the fiber while they're measuring the SAXS pattern. So here's the detector image. It's actually asymmetric. You get a different pattern in the meridional rather than the equatorial. And from all these peaks here, they were able to determine that there is some sort of collagen lattice in there. So it's like this hexagonal lattice of collagen fibers, but the it's this huge lattice, but it's like 20 nanometer lattice parameters, which is pretty big. So there's this. They basically were able to observe this framework of polymers and how they're ordered and how they're tightly folded. And their hypothesis was that they're so tightly folded that they can spring back on release and bring these other cross-linking sites back into register, and they can somehow repair themselves there. So this is kind of neat. Oops. Yeah, there we go. Sometimes users mail us stuff in, and I don't really know what it is, and I'm just sitting there plugging away, measuring it. And sometimes these SAXS patterns, you don't see much at all, but this group sent us a whole bunch, and there was some with like really nothing there, and then all of a sudden there's one with all these rings there. I'm like, wow, this looks just like a powder diffraction pattern that you'd collect with an area detector, right? You get these nice rings, but the scale of it is that the rings or the D-spacings that are here are on the size of like 9 nanometers or 7 nanometers. So it turns out this is a really big lattice of micelles. And so you can just imagine this squiggly water and surfactant lattice that self-assembles there. And I guess they were able to correlate enhanced solvent separation from wastewater at these concentrations where the micelles show up. So they were pretty happy there. They could do some turbidity measurements. They could see something was going on at a certain concentration and relate that to the effectiveness of the surfactant for taking pollution out of the water. But they didn't really know what was going on at the nanometer level, and now they could actually pull that out. So this isn't the actual sample. This is something different. But there's other examples of these micelle lattices out in the literature. How am I doing for time here? I think I'm going pretty fast.
15 minutes.
Oh, okay. Okay, so all those examples were kind of, I mentioned before, there's two origins of the SAXS signal. One is the structure factor, where you can think of this as like, you can pull out the Bragg peaks and do stuff with it. The other part is this form factor. So what you can really consider this as is, think of this thing as a peak itself. This is an integration, but it is actually a peak. And if you go back to your Ewald sphere depiction of diffraction, which peak is this? Well, we're going to really low angles here, really low. So we're actually measuring the 0, 0, 0 peak of the sample, which every sample has. And now we're going to do some fitting and work with that. So yeah, just consider that thing in the middle here as the 0, 0, 0 peak. And I've done some simulated SAXS patterns of some spherical particles of two different sizes. And what you can see here is that this peak here for the large diameter particle is, this is a log-log plot, but it's actually sharper than the signal from the 6 nanometer diameter particle. This is just like the Scherer equation. It's actually related to the Scherer equation. There's information about the size of the particle from the slope, or part of the slope of this first peak here. There's a great paper out from our beam team leader that describes how it's related to the Scherer equation, when you can use the Scherer equation and when you can use this equation to figure out the polydispersity. But okay, so furthermore, what are these oscillations on this peak here? What is all this stuff? It's not Bragg reflections. It's actually related to, you can think of like laser diffraction through a pinhole. You've seen this pattern before, this airy pattern, right? So the first peak there is the width of it is related to the wavelength and also the width of the slit. And by Babinet's principle, the pattern you would get from a pinhole, it would be the same as you would get from like an opaque disk on an open window. You get the same pattern. So just think of it as a Fourier transform of the sample. I've actually done some little Fourier transforms of some bitmap images I made in Microsoft Paint. But here's like a Fourier transform of a small particle, and you get this airy disk, this oscillating function, or a large particle. You get a tighter, sharper central central peak. Now, if you add more particles to the mix and they're spaced out far enough from each other, the contributions just add up. It's the same pattern. It looks a little bit noisy because these are so pixelated. If I actually drew spherical particles, it would look nice. But the contributions just add up. So this is kind of what the form factor part of it is. But there's some limitations to this. And the limits are the solutions. If you want to know about if you want to pull out a particle size from solution or a particle shape from solution, your solutions have to be really dilute. You can't have interparticle effects because when these particles get closer together, they start to interact with one another, and now you get an intense peak here that's related to the interparticle distance, and so the structure factor is taking over, and the form factor you can't really see it as much anymore. This is exactly like the experiment I showed earlier, where if you get these nanoparticles close enough together, you can see a ring that's related to the interparticle distance. So for solution, it has to be pretty dilute. And they also have to be really monodispersed too, and pure, because you're kind of, if you have different distributions, it's like you're only looking at one peak, the 0, 0, 0 peak, and you don't have any overlap of the same peak again and again. So in this simulated pattern here, I've got a bunch of squares and some squiggly lines, and these fringes kind of get washed out. You can't really resolve them anymore. So generally, you need to have a polydispersity lower than 15% to have any hope of seeing these things. So those are the two limits. And then what do you do with this data? How do you process it? So this is the real data for the polystyrene spheres I collected, and you just do modeling and whole curve fitting. I'm really simplifying you here now, but you do fitting just like you would for other diffraction techniques. You build up a model. So I made a model of spheres with a mean particle radius of 50 nanometers. And I actually had to add in a standard or a size distribution until the oscillations kind of washed out, till they somewhat matched the original data here. So what Sigma Aldrich told me was 100 nanometer spheres. It turns out it is that. We use, at the Beamline, we use this Irina and Nika macros from another great software package from APS. It's free, but actually the Igor Pro software that you need to run it costs you money. But this is the one I'm most familiar with. I know there's other ones out there, but basically you need some sort of modeling package to figure out is there particles in there, what is their size, what is their shape. So there's those modeling methods. There's also these data linearization and plotting methods. Like there's Guinier plots, which is where you just plot the log of intensity versus Q squared. You should get if you have spherical particles, you should get a straight line, but they all have kind of conditions you need to follow. You can't just plot your data as log of Q or log of intensity versus Q squared and hope to get something out of there. You have to. There's other things you need to follow. So these are all useful. They're definitely useful, especially this pair distribution function one. But usually modeling is the answer you want. Oh, okay, good. I'm almost wrapping up. So just some examples of using more of like the form factor analysis or the form factor way of thinking than the structure factor one. Drug delivery. So the COVID-19 vaccine is actually mRNA encased inside these lipid nanoparticles. Sometimes they're these liposomes, or they might just be like lipid nanocapsules. And SAXS definitely played a role in characterizing, is the drug, is it inside the liposome? Is it embedded in the layer? Is it on the surface? Is it in there at all? You need to have a really highly characterized drug before it's going to be released to the public. So SAXS definitely played a role in, characterizing these liposomes that were an important part of the COVID-19 vaccine. But it's also, usually it's a complementary method. So they also combine, small angle neutron scattering, dynamic light scattering, cryo-TEM. All this information combined was used to characterize the particles. It's not just there's only so much information in one peak, so it's bound to be low resolution with a lot of hand waving. Okay, the last example I'm going to show is proteins in solution. So protein and macromolecular small angle scattering is actually really big. There are dedicated synchrotron beamlines, not only dedicated to SAXS, but SAXS of biological molecules, because they're such a pain. Usually, you might have a tiny amount of material. There's only so much protein you can get the cells to express. They're all organic. They don't have any heavy, well, usually don't have any heavy metals in them, and they suffer from radiation damage too. So SAXS can be used to, it's usually used to pull out a low resolution shape of a biomolecule that will aid in the solution by other methods like cryo-TEM or X-ray diffraction. But yeah, like I said, we don't do this now. We haven't done it yet, only because no one's brought us a sample yet. If we had a sample, we would try it out. If someone wants to bring protein, I would love to try it. It usually requires some special equipment. There's usually like a flow cell involved, so you're actively flowing material through a capillary so it doesn't get radiation damage, and some size exclusion chromatography so you don't get dimers going in there, so it's very pure. This is an area where SAXS finds a lot of application, and I would love to try it if one of you wants to try it with us. We could both learn together. That kind of brings me to the end. So the main thing I want to say is that we now have a SAXS end station available for users. This was kind of a long time coming, but we have one now. I think it has competitive performance to other facilities, and the users are coming. It's actually exciting to see that. Overall, just remember that SAXS is related to probing relatively big things. We're not going to learn about interatomic distances, but we will learn about big flexible biomolecules or huge lattices or fibers. But it's just an extension of pattern diffraction to a low angle. And the things you can learn about are the packing, just like you can in normal diffraction, particle size and particle shape, but generally not all three at the same time. If you have a really concentrated solution and your particles start packing together, you're probably not going to be able to see these other things. If you have a really dilute solution, well, you're not going to learn about how they pack because they're too dilute. So it's important to always bring a range of concentrations. I don't know what's going to work on the first try, so bring a few. And it's limited in structural information. That's often complementary to other techniques. So it really thrives in combination with microscopy like cryo-TEM or X-ray microscopy. I just want to thank all the Brockhouse team for their help and support. And we do have, I don't know if this is mentioned yet, but we do have a call for proposals that is open now and closes next week. So there's still time to get a proposal together for the next cycle. There's also rapid access proposals you can submit at any time. We really prefer the general user route if you can. So thank you very much.
Thank you, Adam. Questions for him?
You were saying something about form factor and structure factor depends upon the concentration.
Yeah.
What if I have a solid sample?
It's not a killer. Like for example, you can, instead of looking at particles in solution, you can look at voids in a solid, and it's kind of the same thing. If you're looking at something like a solid solution, you want to have like a good contrast between the thing that you're looking at and the matrix that it's in. So having like a metal nanoparticle, like your gold particles and the aluminum oxide support, they're both scattering really strongly. It'd be better to have like gold nanoparticles on a carbon support, so you have a good amount of contrast between the two things. But yeah, solid solutions are not a killer.
Second question is, which software will you recommend to Fourier transform the Q space to pair distance distribution function?
Oh, that you can use Irina from the APS. That was the one I showed. Well, yeah, there. this Irina macro package that can do that can transform your intensity over Q to a pair distribution function, and you can learn about shape that way. But apparently there's other packages. I'm just not familiar with them, but I know they exist. But this one definitely will. You can take your one-dimensional plot, click a button, and it'll spit that out right away. You don't have to do it on your own in Excel or something. But it actually you're at U of S. So you can come to the Beamline sometime, and we can try it on our computer there and set you up, and away you go. Yeah.
So what's the upper limit for Q and SAXS?
It depends on the setup. Again, I'm going to bring up. Well, yeah. So for our particular, the upper limit is how big of a Q, how big of an angle can you accept, how big of an angle you can get out. So for us, it's kind of the edge of this tube here, and actually, if the tube wasn't there, it'd be the size of our detector. So for our setup, the upper limit is 0.32 angstroms, which works out to a D spacing of 2 nanometers. But like if you wanted to go higher, we could move the detector on this table to like a halfway point or something. The closer as we move it in, we can go to higher Q, but we also can't go to lower Q. There are beamlines around the world that do both simultaneously. They'll have their SAXS detector here, and they'll have like a wax detector kind of close by, but not quite clipping the direct beam. So they can do both at the same time. I don't know if we'll ever go in that direction, but if you wanted to go to a higher Q, well, an intermediate kind of Q, we'd put the detector at kind of a closer position. But that's the limit right now. So, yeah.
So can we use the SAXS to calculate the thickness and the property of the surface layer if the surface layer is amorphous, like it mostly contains amorphous?
Well, so you want to know the thickness of an amorphous layer? Sounds like an X-ray reflectivity measurement, maybe.
Like the powder material. It's not a thin film, it's a powder. But then,
And you're interested in the particles under the film, or I'm not sure I understand totally.
like, we are making some composite material that is actually a nuclear-based form. So we are interested to figure out the thickness of the layer, which is the surface layer on top of our material. But then we couldn't calculate that yet because it's like it's very difficult. It's very thin, probably, and then it's also amorphous.
Yeah, I don't know. To me, it sounds like a X-ray reflectivity thing. If you want to figure out layer thickness, I mean, can we do that? Can we do it? We've done X-ray reflectivity before, I think. So I don't think we'd use a SAXS setup to do exactly what you're thinking. We could discuss it after. Yeah.
Both SAXS and reflectivity, they rely on phase contrast of whatever's on your sample. So it won't matter whether it's crystalline or amorphous, but it will see the interfaces because there's a new electronic density there, a different refractive index. So it will scatter in the interfaces. So the more contrast you have, the better.
Sure.
Yeah, I have seen some reports where there was a report found nanoparticle encapsulated in dendrimer. So SAXS was able to identify where the dendrimer is and where the nanoparticle is. So if I have some palladium nanoparticle and there is coated with gold or maybe some other metal, can we identify exactly how much thickness of the gold layer over it and how much the core thickness is?
Yeah, because it's what you're kind of describing is like a core shell system, right? So that I think you already have the answer. That pair distribution of the SAXS.
But I have seen in case of dendrimer and nanoparticles. But if in her case there are both metal layers. Above one is also metal layer, and I don't know the exact metal, so the intensity or the contrast between them is sufficient to get an information about it.
Oh, that sounds challenging. Maybe through modeling you could pull it out. I don't have the answer, but I think that I think the thing you're thinking of with the pair distribution, and that will allow you to determine is it core shell or is it spherical? Is it actually a two-phase system? That's probably, I think you're already got partway there. So
I've seen some core shell tools for modeling inside the Irena Nika. They're
Okay.
probably elsewhere too, but Irena Nika has that one. Now there's so many in SAXS, there's so many parameters that you can change to fit that featureless SAXS curve. That you always need to have a good knowledge of your sample, or you might get a nonsensical result. The fit can be good because you have 20 parameters, but then you have to see if it makes physical sense.
yeah. So.
Any more questions? Well, if not, then we can thank Adam again. That was the last lecture of our school, and now we will head back up to the computer room 367. We have a